In ring theory, we have rings, subrings, and ideals. Ideals are like normal subgroups because they're going to help us instead of forming factor groups, we're going to form factor rings. Subring A of a ring R is called a two-sided ideal. Evidently, there are one-sided ideals as well. If for every element R of the ring and every element A of the ideal, both of these products, RA and AR, are in A. Notice R doesn't have to be in capital A, yet the products are still in capital A. In the lectures, I call this super closed. Super closed. RA and AR get sucked into A. Another slurping sound. Think about it visually. There's your ring R. There's your ideal A. Little a and is in capital A. Little r might be in capital A, but it might not be in capital A. Yet when you multiply them in either order, r times a or a times r, which are not necessarily the same because we're not necessarily talking about a commutative ring here. R times a and a times r are in A. Let's draw them as if they're different. R itself is not getting sucked into A, but by multiplication times elements of capital A, the product gets sucked into capital A. Superclosure. It's almost like it's collapsing the entire ring to A or something. That's not literally what's happening, but it's just kind of a fun thing to imagine. Okay, that's the definition of an ideal, a two-sided ideal. We will only talk about two-sided ideals, not one-sided ideals. Yeah, capital A absorbs elements from capital R. If you define these sets, R capital A or A capital R, which kind of look like cosets, don't they? Though they're not in ring theory. We're going to write ring cosets in ring theory with plus signs. But you can still define these sets. R times capital A is the set of all products, little r times little a, as little a varies over capital A, and similar for capital AR. These are both subsets of A. You might wonder, are they subrings of A? Are they ideals in A? You might wonder that. Let's wait and see. A brief definition, though it's not labeled as a definition, is that an ideal is a proper ideal of R if A is a proper subset, meaning it doesn't equal all of R. All of R is an ideal of R, but not a proper ideal. You might wonder, why is this mentioned? It comes up later in the chapter. Just like there's a normal subgroup test, there's an ideal test. A non-empty subset A of a ring is called an ideal if, first of all, it's closed under subtraction, so it's a subgroup. Actually, we already, yeah, okay, that effectively verifies it's a subgroup under addition. That's like the one-step subgroup test, because the group operation's addition, so that we're using a minus sign for inverses. And this second condition both verifies closure in the subring. A is a subring. That's like the subring test if R is actually an A. But if you only assume R is in capital R and possibly not an A, it is also enough to verify that it's an ideal that's super closed. So yeah, we had a subgroup test in the past. We had a normal subgroup test in the past. Recently, we now have a subring test, and now we have an ideal test. I always found it kind of exciting to use those tests when I was learning it. The subject was like, I'm going to use that normal subgroup test. I don't know, maybe you have no such excitement. All right. Let's look at some examples We're starting right away with the most important example, the most important general example. And that is example 3. Do notice at the start with example 3 that we assume R is a commutative ring. Why restrict ourselves to commutative rings here? Just because it makes things easier. Okay, we could, again, talk about stuff in non-commutative settings, but this will make things easier if we assume R is a commutative ring with unity, in fact. Give me some A and R. This set, that notation looks familiar, doesn't it? Looks like the cyclic subgroup generated by A. Well, guess what? It's not. In more controversy between group theorists and ring theorists. In ring theory, this does not represent the cyclic subgroup generated by A. It might be equal to the cyclic subgroup generated by A, maybe, but not necessarily in ring theory. It's called the principal ideal generated by A. We still say the word generated. It's not, see, if this were group theory here, and R, if we were focused on R as an additive group, okay, as an additive group, if we sort of ignored the multiplication, this would be the cyclic subgroup generated by A. And because of the additive notation, instead of saying this is all powers of A, you'd say it's all multiples of A, where n is an integer. If n is positive, it would mean A added to itself n times. If n is negative, it would mean the opposite of A, the additive inverse of A added to itself absolute value of n times. And if n is 0, it means the additive identity, 0. So if we were focused on R as an additive group, R as an additive group, that's what that notation would mean. N is not a ring element. A is a ring element, n is an integer. Instead of powers of A, we'd use multiples of A. But that's not what this definition is. It's not NA, it's RA, where R is in the ring. And since we're assuming R is a commutative ring, we could say these products are also A times R. Could it possibly equal the cyclic subgroup generated by A? Yes, it could. Why did my news feed come? That was weird. I didn't even touch my computer. That's never happened before that I remember. If the ring is, for example, the integers, if R equals the integers, well, hey, yeah, then NA, where NA means A added to itself n times, and negative A added to itself the absolute value of n times, and 0 in these different cases, would be the same as the ring multiplication, because the ring is the integers. A equals A, and no, the cyclic subgroup generated by A would equal the principal ideal generated by A. But if the ring's not the integers, they're not necessarily the same. In general, they are different. In particular, for example, if R is, for example, the ring of polynomials with coefficients in Z, I'll just say then they are different. For example, as a cyclic subgroup under addition, if I use this notation in the way that I did back in group theory, it would mean all multiples of x as n is an integer. So x would be in there, 2x would be in there, 3x would be in there, etc. Negative x, negative 2x, negative 3x, etc., and 0, and nothing else. But as a principal ideal, can I spell principal? Principal ideal under, I'll just say as a principal ideal, it's all polynomial multiples of x. It's, if you want to emphasize the elements are polynomials, by the way, x is meant to be a polynomial here. I didn't really emphasize that as well as I should have. It's all polynomials f of x times x, as f of x varies over zx. So I'm using function notation here. That's function notation, which I mentioned at the beginning. We don't have to use function notation, but it is convenient. But f of x is a polynomial. It's not just any old function. What does this represent? Really, it represents all polynomials that have x as a factor. This is all polynomials that have x as a factor, which also can be thought of as all polynomials, I should say, with integer coefficients. All polys with integer coefficients that have 0 as a root. If we were thinking about roots. Yeah, with condition, with integer coefficients. Integer, I can't spell today. Integer coefficients. With ring and field theory, our main application, you might say, is going to be trying to think about factoring, which sounds like, you know, that, why is that a big application? I mean, isn't that, you know, 9th grade math or something? Well, no, factoring is hard. Yes, you teach factoring to, say, 9th or 10th graders, but you keep it to pretty limited circumstances, like quadratics that are relatively easy to factor, maybe cubics that are relatively easy to factor. A little overlap with numerical analysis. There are other theorems. There's the fundamental theorem of algebra that says any polynomial with real or even complex coefficients has at least one complex number root, which could also be real. And that can be generalized to say if the degree is n, you've got n real or complex roots counting multiplicity. There's also something called the rational roots theorem, which I did mention in numerical analysis, and we'll talk about in here. But there's other theorems that can help you think about factoring, and in particular, when a polynomial cannot be factored with certain kinds of restrictions on the nature of the roots. That's how ring theory developed back about 200 years ago. Galois, which is spelled that way. Don't say Galois. Galois and Abel abelian is in honor of Abel. Back about 200 years ago, about the 1820s or so, they were studying equations. Their goal was to think about solutions of equations. Linear equations are solvable. Quadratic equations are solvable with the quadratic formula. Cubic equations are solvable. There's a cubic formula. Quartic equations are solvable. There's a quartic formula. You do not want to see it. But somebody came up with a quartic formula. It is incredibly complicated. People wondered, what about quintics? Quartics are this complicated. Do we really want to even try quintics? Nobody was successful. People wondered, is it possible to prove that quintics cannot be solved with, and by solved, I mean with arithmetic operations and roots and that kind of thing. In the general case, not special cases. Special cases sometimes can be solved, but in the general case, can you solve quintics? And the answer that Galois and Abel found was no, you can't. And in fact, quintics in higher degrees are impossible to solve in the general case. Doesn't that contradict the fundamental theorem of algebra? Well, the fundamental theorem of algebra says there are roots. You, in theory, can solve them in the sense that there are roots, but that doesn't mean you know what they are. The roots exist, you just don't know what they are. You can't write them in terms of simple expressions. As far as I know, Galois and Abel didn't talk. Maybe they did. They're actually both very young. Galois died young in a duel. He was shot in a duel. It was either over a woman or it was politics. I forgot. One of the two. He was shot when he was like 22 or something. But he done all this amazing math. And Abel was fairly young when he was doing this too. I think he died fairly young too, but not as young as Abel. Or it's Galois. Galois was also French, so maybe that had something to do with it. I don't know. Anyway, yeah, Abel was Norwegian. Anyway, where was I going with that? That's our main application, you might say, of ring and field theory. Did we have a main application in group theory? Studying groups. Is that the main application? Group theory does have applications to crystallography if you want to get fancy. More basic application is to, like, you know, UPC codes and ISBN numbers and things like that, check digits. Cryptography, though you could argue that's just number theory. Ring theory and field theory, we are working towards an application, okay? Understanding factorization of polynomials. So, coming back to this example, with principal ideals, this could be thought of as either of these sets. All polynomials with integer coefficients that have the polynomial x as a factor, which is equivalent to all polynomials with integer coefficients that have 0 as a root. Okay, so it's related to root finding. That'll be a big deal for us. Ideals are important for factor rings. Okay. What is a factor ring? It's like a factor group, except it's a ring. Let R be a ring, let A be a subring of R. The collection of cosets, notice the additive notation. R plus A, as R varies over capital R, is a ring under the operations of coset addition and coset multiplication. This is the same operation as a group, just with additive notation. Add the representatives. Add two cosets, S plus A and T plus A, by adding their representatives to get the coset S plus T plus A. You multiply in the same kind of way, the way you would guess. Multiply the representatives. Notice I'm not foiling here. There's no A squared that happens. Okay. And I don't get SA and TA either. I'm multiplying coset, the coset representatives, the S and the T. But again, with factor rings, we use additive notation. It's not shown here, but we still do use the same kind of notation for a factor ring. Like that, almost as if it's a fraction. Say R mod A for short, or the factor ring of R by A for long. Okay, there are some examples. Let's study at least one of these examples next in depth. How about study example 11? Consider this factor ring, Z3X mod the principal ideal generated by x squared plus 1. Before we look at this example, based on what we just said a few minutes ago, think about that principal ideal generated by x squared plus 1. That would be all polynomials in not Zx, but Z3X. It's an infinite polynomial ring, but it's got a characteristic of 3. Coefficients are either 0, 1, or 2. All polynomials in Z3X that have x squared plus 1 as a factor. When you see that kind of principal ideal notation, and by the way, when we're doing ring theory and you see this notation, it's assumed that we're talking about the principal ideal, not the cyclic subgroup generated by the element. This thing that we're modding by, this principal ideal, by the way, you do need to prove principal ideals are actually ideals. You do need to use the ideal test. Something you should be able to do on the exam. It's all polynomials in here that have x squared plus 1 as a factor. Does x squared plus 1 have any roots in Z3? No, it doesn't. The elements of Z3 are 0, 1, and 2. 0 is not a root. Z squared plus 1 is 1, not 0 mod 3. 1 is not a root. 1 squared plus 1 is 2, not 0 mod 3. 2 is not a root. 2 squared plus 1 is 5 mod 3 is 2, not 0. 0, 1, and 2, the elements of Z3 are not roots of x squared plus 1. Why am I restricting myself to Z3? Because it's Z3 right there, that's why. This polynomial, it turns out, because it doesn't have roots in Z3, is not factorable over Z3. It's called irreducible over Z3. And that's going to make this factor ring special. And we'll see. File that comment away. Continuing. Okay, to simplify notation, let that ideal be called I. By definition, the elements of R have this form where f is a polynomial in Z3. Right, that's the definition. And by the way, being an ideal is necessary to prove multiplication is well defined. If you look at the proof of this, the main thing they're trying to do is show that multiplication is well defined. That's the conclusion there. Well defined comes back. Being an ideal is necessary for that to happen. So this is an ideal, this is a factor ring. But the important question is, what do the distinct cosets of R look like? Remember, when dealing with cosets, you can have different representatives. Maybe there's a finite number of cosets. Is that possible? No, it'll be still infinite in this case, but a priori, before the fact, it could be possible. Okay, here's the key observation. This is really important. The fact that x squared plus 1 plus I equals 0 plus I means that when dealing with coset representatives, we may treat x squared plus 1 as equivalent to 0, and therefore x squared is equivalent to -1. Even though -1 is not in Z3, well, it's still convenient to use a -1. But realize in Z3, -1 equals 2. Right, mod 3. So when writing x squared equals -1, it really is meaning x squared equals 2. But it's convenient to use -1 and just do our modding at the very end. Why is this true? Why is x squared plus 1 plus I equal to 0 plus I? It's just a plain coset property from group theory, actually. It's this one. AH equals H if and only if A is an H. right? That's property of cosets. That's all that's going on here. X squared plus 1 plus the principal ideal generated by x squared plus 1 equals the principal ideal generated by x squared plus 1, because x squared plus 1 is in the principal ideal generated by x squared plus 1. That's why. That's essentially this property. Wait, is it? This is acting like the H. Isn't this like EH? Yeah. And this is the same as 0 plus the principal ideal. So yes, this does equal this for this example. And so like the author then says, x squared plus 1 in the factor ring is equivalent to 0. They both represent the same coset, the identity coset, in fact. The additive identity coset. So when we treat x squared as if it's equivalent to -1. For example, that helps you simplify other cosets. Here's a real key calculation. 2x squared plus x plus 1 simplifies to that. What happened? That x squared can just get replaced with -1. I mean, you really have to prove that this is okay, but you can. And we won't bother. You can replace this x squared with -1. So you get 2 times -1 is -2. This 2x squared got replaced with -2. -2 plus 1 is -1. So I could write this. The author didn't mention it, but of course that could also mod 3 be written as x plus 2 plus I. And that probably would be the way I would prefer to do it as a default. The author didn't bother doing. So we're talking mod 3. This would be the same as x plus 2 plus I. Maybe you want to make a little note to yourself right there if you have your book open. It's page 282. Moreover, when dealing with coset representatives, x squared equaling -1 implies multiply this equation by x. It implies x cubed equals -x, and x to the 4th equals 1, right? Multiply both sides of the equation by x. You get x cubed equals -x. Square both sides. X squared is x to the 4th, -1 squared is 1. Is that right? Well, in ordinary math, -1 squared is 1. Is it in mod 3 arithmetic? -1 squared is the same as 2 squared. 4 mod 3 is 1. Yes, it did work. So you could simplify this coset like that. Replace x to the 4th with 1. Replace x cubed with -x. Replace x squared with -1. Leave the 2 as is. Combine like terms. The 1's cancel. Left with -2x plus 2. And here the author did mod by 3 at the end. -2x got replaced by x, because -2 equals 1 in Z3. I don't know why the author did it there, but not there. Maybe an oversight on the author's part. Joke out. Continuing, if I take x to the 4th equals 1 and multiply both sides by x, I get x to the 5th equals x. Multiply both sides by x again, I get x to the 6th equals x squared. Typo there. Should be a comma, I think. Oh, no, okay, that's not a typo. X to the 6th equals x squared times x to the 4th. I mean, you could say x to the 6th equals x squared. That's true still. After multiplying this equation on both sides by x. But it's also true that x to the 6th equals x squared times x to the 4th. I mean, x to the 4th was 1. X squared is -1, x to the 4th is 1, so this is -1, which is 2. And so on. You can take any coset of this form and simplify it to something of this form is the point. Where A and B are in Z3. I said something wrong 5 or 10 minutes ago, actually, then. It's not infinite, it is finite. It's a finite ring. How many elements? 3 times 3, 9. 3 choices for A, 3 choices for B. It's a finite ring. Is it a field, possibly? It actually is a field. Have we proved that? No. I think it's probably worthwhile, and this will be the last thing we do with this example, and then we'll do a little bit more before we end today. Well, maybe we should try to find the multiplicative inverse of some element. I put problems like this on exams before. What is x plus 1 plus I inverse in this factor ring, which I'm telling you is a field? What would you do? Here's what I would do. I would multiply times an arbitrary element of the factor ring, which happens to be a field, and ask what conditions on A and B will give me the multiplicative identity, 1 plus I. Multiply the representatives. And yes, you would FOIL this out. You'd get AX squared plus BX plus AX plus B. Now here's the trick. Replace x squared with -1, just like in the example. It's almost like this is the complex numbers, almost, except it's finite. Maybe it's like a Gaussian integers kind of thing with finite coefficients, finite possibilities for coefficients. Replace x squared with -1, simplify. Looks like it simplifies to this, right? Set this equal to the multiplicative identity 1 plus I. And ask what conditions on A and B will make that true. Are there conditions? That's equivalent to A plus B equaling 0 and B minus A equaling 1. Does such a system of equations have a solution when A and B are either 0 or 1? It doesn't seem like it, does it? Oh, wait, no, not just 0, 1. 0, 1, or 2. How about B is 2 and A is 1? In Z3 is a solution of that system of equations, right? Yeah, that works. So evidently, is that you might wonder if that's the unique solution, and it would have to be, but I won't prove it. Evidently, the multiplicative inverse of x plus 1 plus I is A is 1, B is 2. X plus 2 plus I. Unexpected, but that's what it is, it seems. Okay, we could check by multiplication as well. Maybe I should do that. x plus 1 plus I times x plus 2 plus I. It's x squared plus 3x plus 2 plus I. 3x is 0, x squared is -1. This simplifies to 1 plus I. 3x is 0 because the coefficient got modded by 3. X squared is -1 because we're in this factor ring, not the original ring, not Z3x, the factor ring, which does happen to be a field that turns up. Okay, since we're low on time and we want to end early today, I think we only have time to summarize some things, but I think this will be helpful. This definition is a twofold definition, prime ideals and maximal ideals. Definition doesn't seem that hard, but trying to come up with examples on your own would be hard of these things. A prime ideal A of a commutative ring R is a proper ideal. Notice the word proper there is in there. It was briefly defined at the beginning of the chapter. With the property that if the product of two numbers is in the prime ideal, then, not numbers, two elements is in the prime ideal, then one or the other element is in the ideal. Is there a reason it's called a prime ideal? Yes. If R happens to be the integers, and A happens to be, the principal ideal generated by, say, 5, the integer 5, which would be the same as the cyclic subgroup generated by 5 because we're talking about the integers, and would be all multiples of 5, 5, 10, 15, 20, etc. 0, -5, -10, -15, -20, etc. Then what you're saying is if the product of two numbers is a multiple of 5, then one or the other of the numbers is also a multiple of 5, isn't it? That's what you're saying. Is that special with 5 being prime? If something's a multiple of 5, it means 5's a divisor of the number of the product. Euclid's lemma, if P divides A times B, where P is prime, P divides A or P divides B. If 5 divides A times B, then 5 divides A or 5 divides B. This is the Euclidean lemma. Euclid's lemma. In chapter 0. You may have forgotten Euclid's lemma. Fundamental fact about primes. And if your principal ideal is not generated by a prime, this will not be true. Maximal ideal. For sake of time, I'm going to skip that at the moment, that definition. You could draw a picture. I'd recommend drawing a Venn diagram kind of picture, a blob picture to try to understand this. It's not an easy concept, but these theorems, theorem 14.3 and 14.4 are pretty important. In a commutative ring with unity, the factor ring is an integral domain if and only if A is not a prime number, but a prime ideal is what that means. But we just say prime for short. And in the same setting, the factor ring is a field if and only if is a maximal ideal. That's a real quick summary of some pretty challenging things. You should study it in depth. Study both the examples and the proofs. The proofs are long enough and hard enough that I probably wouldn't put the entire thing on the exam, but you should study them enough that you could understand pieces. They're two directionals because they're if and only ifs. Maybe you should be able to do like one direction on an exam if I gave you some hints. Think of it that way. They're not easy to come up with on your own, but they are understandable to study. And if I gave you some hints, you should understand them well enough that you could reproduce them with the hints. And very briefly, chapter 15 is about ring homomorphisms. You knew it was coming, right? If there's factor groups and they're related to group homomorphisms, factor rings must be related to ring homomorphisms. What's the definition of ring homomorphism? It's operation preserving mapping. You got to preserve both addition and multiplication. It's doubly operation preserving. Is there such thing as a ring isomorphism? Yes, if it's also 1-to-1 and onto. Similar kinds of properties hold. Long list of properties. There's a first isomorphism theorem for rings. There it is. Very similar to the one for groups. More importantly, over the weekend, really study the examples, and I would say especially examples 4 and 5. Example 4, we determine all non-zero ring homomorphisms from Z10 to Z20 and from Z20 to Z10. Not going to take the time to read this, but it's something you should study well. And various theorems are being used, as well as notation from group theory. This is group theory notation because we're talking about theorem 4.2 there. This is the order of an element as a group element in the ring. Evidently, orders of elements in groups are still relevant. Something else to note here is in rings, when it's not including when we're not talking about 0 or 1, you can have this property. A times A can equal A. A squared can equal itself. A squared equals A. Including when A is not 0 or 1. I mean, certainly 0 squared equals 0 and 1 squared equals 1. But at least in non-integral domains, A squared can equal A even when A does not equal 0 or 1. Such an A is called, got a name, it's called an idempotent. I love that word. There's also nilpotent elements, nilpotent and idempotent elements. I think I do talk about those in the lectures in more depth than I'm doing right now. Okay, something else to take note of. Study really well examples 4 and 5 especially. Okay. All right. Have a good weekend.